Who's leaving and rejoining? Oh, there he is. So, this is a question. Oh yeah, if you didn't see last question, I did go over. I did manage to find and fix the error. It was just a signage error. So the process is the exact same. I just accidentally flipped a sign. I've re-recorded the end of that video, so it has the correct answer there. But just to make it clear, also in the video you can see the MultiSim output and the MultiSim problem. Do question 5 first. Okay, we'll do question 5 first. So, question 5. For the circuit shown in figure 5, complete the following. Calculate the total apparent power, total average power, total reactive power, total power factor, total impedance, and the RMS value of Vs. Okay, so first thing we're going to do is we're going to group this impedance block here, 1 plus 0.2J, into its own block. So we can treat it as its own single sort of impedance, right? 1 plus 0.2J. Makes it simpler. That's it. So, to find the where's my ping ISO to Eggman? That's okay, you missed nothing. You missed nothing. The series and parallel impedance works the same way as resistors. Yes. So, what do you call it? Inductors, resistors, and impedance all work the same. That is, you add in series and you do 1 over 1 plus 1 over the other, all to the power of -1 in parallel. Capacitors is the other way around. That's it, pretty much. Capacitors that are not written in this format, right? If it's written in J, then you just add like any resistor. If it's written in farads, then you flip it around. So this here is 1 plus. Is that clear? Because I probably should have explained it better. Okay, so resistors, inductors, and any impedance written in form A plus BJ, you just add. Series, add, parallel. Oop. You flip that around, or you do this annoying thing. Which is the same thing if you're confused, as xy over x plus y. These two are the same. Capacitors, flip this around. So series, you do that, and parallel, you add. So, anyway, question 5. Calculate the total apparent power. So to find the total apparent power, you have to add all of the power being absorbed by everything. It doesn't matter if it's parallel. It doesn't matter if it's series. And that pretty much makes sense. You're basically asking how much power is being absorbed by each one of these. And by conservation of energy, you have to you just add them all up. What happened to question 4? I'm doing that after. I'm doing 5 first. Yeah. So we need to find the total apparent power of all 3 of these. Let's start with this one on the right. So what we know about this question, let me just take a screenshot of it so I can see. Yeah, we finished the Thevenin question in 15 minutes. You should be able to do it that fast on the exam. If you're not, you're failing. Alright, so we're given 60,000 voltage amps at 0.6 leading across 240 with a phase of 0 VRMS. This is passive. So, yeah, it's passive. So, we construct the power triangle, right? Actually, before we do that, we need to convert this leading, the 0.6 leading, into something that's a lot easier. So the formula for this is just cosine -1 of uh of this 0.6. Oops, yeah. And because it's leading, you add a negative sign. If you had 0.6 lagging, you do not add the negative sign. Like this. That's lagging, this is leading. And if you do that, you get that this is, let's see, negative cosine inverse of 0.6 is negative 53.13 degrees. So let's construct our power triangle here. You can draw your power triangle as large or as small as you want. It doesn't matter. This angle here is negative 53.13. This here is 60,000 voltage amps. So in case you don't know, watts is the real component. The real component, also known as the power, just the average power. Voltage amps is the complex, or the apparent power. And voltage amps resistance is the imaginary power, or the reactive power. So just remember that, right? You kind of have to. There's not an easy way to remember, in my opinion. So this is 60,000 voltage amps. Now the really cool thing is you can actually just put this into your calculator. So 60,000 with a phase of negative 53.13 and put it into rect format. And it will literally just give it to you. So this is 36,000 watts. And this here is negative 48,000. I'm just going to put K voltage amp resistance. Let me just make this a little bit tighter here because I'm going past the border here. How do you do that? Just put in your calculator 60,000 with a phase of negative 53.13 degrees. And turn that into rect form. If you forgot how to do that, on the FX991ES, it is shift 2, so shift 2, and then 4. And that selects A plus BI. And once you put that in your calculator, it will just spit out the real component. It'll spit out 36,000 minus 48,000 J. Remember, this is your imaginary, right? So, negative 48,000. This is your real component, 36,000. You can also just do it. It's a triangle, right? You can just use trigonometry to solve it. But your calculator does it automatically for you. Why go through the effort? So, this is our power triangle for our first question. Now, or the first block here. Now, how about the second block? Well, first of all, let's notice that this here is one node entirely, and this node here is one node entirely. This is 0 volts. We're going to say that this is the ground. So this here is 240 voltage RMS, right? Which means that the voltage drop across here is also 240 with a phasor of 0 V RMS. There's a phasor 0 in there. So the voltage here is the exact same thing as this, right? If you remember from the start of ELE202, when it's in parallel, they have the same voltage. Sorry, yeah, when they're in parallel, they have the same voltage. So the data for this one is 30,000 voltage amp resistance and 40,000 watts with a voltage of 240 with a phasor of 0 VRMS. So we can assemble our power triangle as always, right? We have a positive wattage and we have a positive reactance. Let me make this a bit smaller. Remember, this is reactance, or the imaginary component. So this is 30,000 VAR. This here is 40,000 watts. And we have, and then we have our hypotenuse, or apparent power. Once again, just put it in your calculator. Put in 40,000 plus 30,000 I, right? Because this is your imaginary component. You have to add I. And if you turn that into phasor form, it will give you your hypotenuse, 50,000. Let me just write 50,000 VA. And your phase, which is 36.887 degrees. So there you go. That's how easy it is to make the power triangles. It's not too hard. So get used to that. I think you just need to get used to how to use it on your calculator. But once you do, it's fine. You're done, really. However, here comes the harder part. We have a third part here. This combined 1 plus 0.2j. So we need to find the power output of this thing, right? Now, if you remember, the formula for the apparent power is sorry. Can you explain how you got the angle again? For the first one or the second one? This one or the second one? You just put in your calculator. This is also just a triangle. You can use tangent or tan inverse, or is it tan inverse? Yeah, you can use tan inverse, or you can just put in your calculator. The way that I did it in my calculator is I just put 40,000 plus 30,000 J, or I, and I put it into phasor form. And when you do this, this is your hypotenuse, and this is your angle. So if you put this in your calculator, you'll get 50,000 with a phasor of 36.87. Remember what a phasor actually is. A phasor is just the hypotenuse, or the magnitude, which is a hypotenuse, at an angle. And the rect format is just the XY components of it. So, where was I? Right. Yeah, here. So, we need to find the power output of this. We write the apparent power. And when you need to find apparent, average, and reactive, focus on apparent power, because apparent power contains the other two. So the apparent power is going to be VRMS, IRMS, the magnitude of each, at a phase angle of the theta of the phase angle is a phase angle of VRMS minus the phase angle of IRMS, like so. So we need to find the voltage across and the current across. Well, we can find the current because we can use this note here, right? We can use Kirchhoff's current law, right? This is getting a little bit crowded, so let me just remove this. The current here is being split two ways, right? So it looks a bit like this. This is I. This is I that we want to find. This is I1 and this is I2. So I is equal to I1 plus I2. Let's give this a name. Let's name this a third one. I3 is equal to I1 plus I2. So can we find I and I2? Actually, as a matter of fact, yes. Because because of this exact same thing as well. It is that the formula here is that the apparent power, or the magnitude of the apparent power, is equal to the magnitude of VRMS times the magnitude of IRMS. Right? We know VRMS. We know the apparent power. We can find IRMS. Let me just move this a bit down. Here you go. So this becomes S divided by VRMS is equal to IRMS. So do that in your calculator. You get 60,000 divided by a voltage of 240 is equal to 250. Now what's the phase angle? Because we need the phase angle, right? Well, remember that the phase angle for S, the second equation is the phase angle for S is equal to the phase angle of voltage minus the phase angle of the current. The voltage here is 0, right? So we can just skip that out. And so we get that the phase angle of so therefore that the phase angle for I is equal to 53.13 degrees. So let's put that phase angle in here. 53.13 degrees. And now let's find the current here. It's the same process, right? It's the magnitude of the apparent power divided by the magnitude of the VRMS is equal to the magnitude of IRMS. How did I get 250? Here you go. S is 60,000. VRMS is 240. This bar on the top here means magnitude. Or at least I'm using it for magnitude. It should be magnitude, I forgot. But in this case it means magnitude, yeah. That would be for the first one, right? Yes. So I'm just finding the first one here. Because, yeah, you have to do it for the second one as well. So this is the first here. That's a bad one, first. And this is the second one. So for the second one, you do V divided by, S divided by VRMS. S is 50,000. Divided by VRMS, which is 240. And you get 208.33. And again, the theta S is equal to theta V minus theta I. Theta V is 0. So therefore, this is negative 36.87 degrees. So, we know here that I1 going this way is 250 with a phasor of whatever, and this one going down is whatever. So I3, the current running across this impedance, is going to be the sum of that. Let's find R3. So this is going to be third. IRMS is equal to I1 RMS plus I2 RMS, which is equal to 250 with a phasor of 53.13 plus 208.33 with a phasor of negative 36.87. By the way, I'm doing this, if I'm doing this like a little fast or I'm skipping ahead, you feel like, tell me, because I'm mostly trying to get through most of the busy work, but I don't know if I lose you or something. So if you feel like I'm losing you, then say something. Feel free to. Which number is for 208.33? It comes here. So the how do you get 208? Here. So it's the apparent power divided by the voltage. So this is the apparent power, right? This is S. The imaginary part is Q, and the real part is P average. When I plug in my numbers for calculator for magnitude and angle, I get a different angle for IRMS. Yes, because the formula is not. Here's one of the things that really trip you up. The formula is not that the apparent power is VRMS times IRMS. The formula is that the magnitude of the apparent power is a magnitude of VRMS times the magnitude of IRMS. This is just for the magnitude. The angle for S is the angle of the voltage minus the angle of the current. So yeah, you can't just multiply VRMS and IRMS together in complex form. You won't get the right answer. So I'm just going to let's do a list of very important formulas at the top here, right? Because I think that will help clear some confusion. So, real is associated with watts, also written as P average or average or total, average power. The imaginary component is written in VAR. It's given Q, and it is the reactive power. And the complex, the combination of the real and imaginary, is VA. We give it S, and it is the apparent power. It's a lot of names that are all different but associated with each other. And of course, if in case you forgot, VRMS is equal to V divided by root 2, and same with IRMS. That's I divided by root 2. So that is I believe that's a formula. Let me see. Someone correct me if I'm wrong. But from what I remember, those were the formulas. Let me just take a look. Because, yeah, I probably should have written it down somewhere, but... Yeah, okay, so the apparent power is this. If you only have the actual voltage, it's 1/2 VI. Yeah, VI. Like that. Okay. So, the third box. It's IRMS is equal I1 RMS plus I2 RMS is equal to this. Let's plug that into our calculator. We have 250 with a phasor of 53.13 plus 208 with a phasor of negative 36.87. IRMS is, there you go, 325 with a phasor of 13.32 degrees. Let's four significant digits. Honestly, I play really fast and loose with my significant digits. You should probably go to 4 significant digits on an actual evaluation. So, let me just write the third box here, right? So that is this here, 1 ohm and 0.2 J. So therefore, the impedance is 1 plus 0.2 J. And remember, V is equal to IR. And the same rule applies with RMS. So V RMS is equal to I RMS R, or Z in this case. You could prove that because that would just be if you have V is equal to IZ, if you divide both sides by root 2 to get RMS, those two cancel out. You get V RMS is equal to I RMS times Z. So we know impedance, we know current, so we could find the voltage. And the voltage here is going to be 325.4 with a phasor of 13.32 times the impedance, 1 plus 0.2 I, or J. I need to set my calculator in polar form. I left it on rect. Anyway, 331.8 with a phasor of 24.6 degrees volts. That's our VRMS. And now, we can now use our power formulas, right? Remember? The whole reason we did this is because we needed to find S, which requires VRMS and IRMS. So S is equal to 331. Let me write down the formula here. It's VRMS, IRMS, and theta S is equal to theta V minus theta I. So the magnitude of S is going to be 331.8 times 325.4. That's 108,000. And then the angle of our apparent power is going to be our voltage angle, 24.6 minus 13.32. That's 11.28 degrees. Let's construct our power triangle. So we have this here. Again, the power triangle is never going to be to scale. It's just meant as a representation, right? 11.28 degrees. This is S is equal 108k voltage amps. And now, again, do that trick that I showed you. Do 108,000 with a phasor of 11.28 and put it into rect form. And it will give you 105 or 106,000 plus 21 125 J. Is that correct? Wait, I may have... What the hell? Oh, no, that's correct. Yeah. So, this is going to be 21,125 voltage amp resistance. It's going to be 106,000 watts. You have a question? So, now in this question, we've gotten the power absorbed by all three of these. And so we know the total power running through the circuit. Can you screenshot that and put in chat? You want the... Okay. Again, I'm going to be uploading this PDF afterwards. You basically fucked connecting. You mean like... Oh, you're at work. Okay, I see. Yeah, I will be uploading everything. Don't worry. Good luck at your job. So, what's the apparent power, or the total apparent power? Because that's what our question is asking. Let's actually drop down the question here. Calculate the total apparent power. The total apparent power is just the sum of all of the powers. That's it. In complex form, by the way. So we can do that the sum the total is 108,000 with a phasor of 11.28 degrees plus this one is 50,000 with an angle of 36.87 plus, and our first one is 60,000 with an angle of negative 53.13. All you do is put in your calculator. You just sum up all of the power consumption. So that's 108,000 with a phasor of 11.28 plus 50,000 with a phasor angle of 36.87 plus 60,000 with a phasor angle of negative 53.13. And, oops, I put that into rect form again. You get a total of 181,940. There's going to be some rounding issues, yeah. But that's pretty much 182,000. With a phasor angle of... Did I put it in wrong? I did put it in wrong. 1 second. 36.87 times 60,000 negative 53 dot. According to my math, I got a different answer, but I can't figure out why. Let me try it again. Sorry about this. What the hell did I do? You got 157,000? The answer that I wrote down here is 144,000. But, putting in my calculator, I'm getting 182,000. So let me just make sure that I've put in all my numbers correct. So that's 108,000. The phasor angle of 11.28, yeah. Plus 60,000. Plus minus 53.13. Right? Oop, let me see here. 60,000 with a phase angle of negative 53.13. Plus 50,000 with an angle of 36.87. Yeah. Yeah, I think it's 182. Maybe I must have done something wrong in the calculations, or in my previous calculations. Okay, so you get 182,000 with a phasor angle of actually around 1 degree. It's pretty low. 181. Let's do the whole thing. 181,944 with a phasor angle of 0.98 degrees. So now let's find the total average power. And the total average power is, again, it's just a sum of all of your other numbers. So here we have 106,000 plus 40,000 plus 60,000. You get 206,000. 206,000. Okay, now I'm getting very confused. Man, I always manage to screw up. I don't know how. Oh, did I put this in wrong? 1 second. 108 with a phasor of 11.28. 106,000 plus 21,000. Is someone starting a goddamn... Alright. 1 second, let me just compare these numbers. So this is 30,000 plus, or minus 48, plus 21. It's around okay, so that part... Yeah, the power average is, it should just be the real part. So that should be 106 plus... I'm suspecting yeah, it's 106 plus 40,000 plus 36. Oh, I put in the wrong number. Sorry. So if you do that, you get 182,000. It's because of rounding rules. These are nearly identical. If you did it out to a couple digits, you'll get a difference. You really should be doing like 4 digits of accuracy. Again, I'm being really fast and loose. So this is more about, but yeah, it's pretty much 182,000. And if you do the reactance, so this is the Q, again, you sum up all of the imaginary parts. Our first one here is negative 48,000 plus 30,000 here plus 21,125. And you get 3,125. Again, this is watts. This is VAR. And you would write down the final apparent power as a magnitude. So that's 182,000 VAR. You're in radians mode this entire time. Yeah, that would do it. I'll be completely honest with you. I got so paranoid of that. I got into the habit every single time I started a test, I do sine 90. Because I know for sure what it should be, whether I'm in radians or degrees. Okay, yeah, so I was right. It is this number, if you add them all up. I guess in my my work, I screwed it up. So, this is... so this here is our average power. It's in the name, right? This here is our reactive power. And this here is our apparent power. So there's 1, 2, and 3 down. So just to review what we did here, right? We went through each... We took our circuit. Apparent should be VA. No, not VAR. Did I... Silly me. Yeah, that's VA. Thanks. So the so we went through each load here, right? And given the information, we turned it into the power triangle, right? For the first one, we're already given the apparent power and the leading amount. You convert that to an angle using cosine inverse. Let me just leave a note here for anyone reading afterwards. 0.5, or sorry, 0.5 leading. Degree of the apparent power is cosine inverse of 0.5. And 0.5, negative. Lagging is the opposite. So we assembled our power triangle using the given information. In this case, it's given in form magnitude and degree. If it's leading, the triangle points down. If it's lagging, the triangle points up, right? Yes. You can see here I can pull up the notes from the from Mariam. Yeah. So when it is lagging, it's up. When it's leading, it goes down. Um yeah, so we went through the second one. The second one we were given the components, right? We're given the imaginary part and the real part, and we can find the magnitude and the angle from that. That's just trigonometry. Again, review trigonometry from grade 9, 10, 11, 12. The third part, we're given just the impedance. That's the name, impedance, yes. And so, using impedance, voltage and current, we find the power. We can use that to find the power. Sorry, we find the voltage. We use the voltage and the impedance to find the. Sorry, I did the other way around. We find the current. We give using the current and the impedance. We find the voltage, and using the voltage, we find the apparent power. And again, once you have the apparent power and the angle, which you can find from voltage minus current, you can make your triangle. And then we just add them up. That's it. There's 1, 2, and 3 down. Now calculate the total power factor. Power factor is equal to what? Power factor is actually this exact same thing here. Right? So, let's assemble our total power triangle. It looks a little something like this. 182,000, 3,125, and 182,000. Now, if I was diligent, I would have gotten a difference between these, but I dropped a lot of numbers. I was like 2 digits of accuracy, so they're very close. Let's take this instead, because it's right here. This is the angle. It's about 1 degree. And so if you have let's calculate these exactly. So let's do 108,000. Actually, no, I can't because I literally would have to redo everything. Point is, this is 1 degree. Then you do that is it cosine? Yeah, so then you do that the power factor is equal to cosine of your angle, S. Or it's equal to the cosine inverse of your cosine inverse of your adjacent over your hypotenuse. Is that correct? Oh no, it's just your adjacent over your hypotenuse. So these are the two ways of finding power factor. They're both the same. And you'll get, in this case, at 1 degree, it's 0.99985. It's incredibly low. Which is also why I got literally the same answer, because I wasn't accurate enough. Now, this points upwards. You have a positive degree, so this means that it is lagging. So you write down that the power factor is 0.99985 lagging. And you can verify that by turning that into a degree again. You do cosine inverse of 0.99985. 0.99985 is about 1 degree. You actually get 0.992 degrees, but So there's your power factor. Calculate total power factor. Now, calculate the total impedance. This is actually, we could use the exact same formula here, right? You remember that V is equal to IZ, right? So let's go here and find Z. So that's V over I is equal to Z. V RMS over I RMS is equal to Z. We know the voltage, we know the impedance, or we know the voltage, we know the current, we can find the impedance. The voltage here is 240 with a phasor of 0, divided by the current, which is 250 with a phasor of 53.13 degrees. And so that impedance here, let's put that in rect form, because we usually do impedance in rect form. 0.576 minus 0.768 I. Then we can do the impedance here. Again, VRMS. VRMS over IRMS equals Z is equal to, again, same voltage of 240, but the current here is 208.33 with a phasor of negative 36.87. And you'll get 0.922 plus 0.691 J. Running out of room there. And the impedance here we already know. So let's reconstruct this circuit. So we have our voltage source here. We have our first Z load, which is 1 plus 0.2 J. Z load as in impedance load. We have our second load here, which, let's just put these first. Like that. Let me just copy this so I can see. So this is negative 0.576 minus that, and this is that. Actually, it should be the other way around. Oops. It doesn't matter. They're in parallel is the point. At this point, this is just circuit reduction, right? So these two are in parallel. Negative 0.576 minus 0.768 I in parallel with 0.922 plus 0.691 J. Oh, this should be J, yeah. Plus 1 plus 0.2 J. So the impedance total. That is one hell of a formula. So let's do it. So it's negative 0.576 minus 0.768 I to the power of negative 1 plus 0.922 plus 0.691 I to the power of negative 1, all to the power of negative 1. You know how to do this. This is just reduction. Just to make sure everyone knows, though. 1 second. Plus 1 plus 0.2 I. Just to make sure everyone knows, though, when they are in parallel, you just do the impedance of the first one to the power of negative 1 plus the impedance of the second one to the power of negative 1, all to the power of negative 1. Or Z1 times Z2 over Z1 plus Z2. They both give you the same answer. Should anyway. So if you do that, you get total. Hello, I am recording this in post because once again, I have severe calculator deficiency. I copied this number wrong. I accidentally put a negative in front of it. I'd be very concerned if you have negative resistance. Please tell me how you would do that. But if you don't do that and you do the math properly, you will get that the Z total is 1.72 plus 0.029J. Now that's your answer for Z total. How do you find the RMS value of VS? There's two ways you can do it. The first one is recognizing that our circuit, it does have a parallel, but we can ignore the parallel for voltages. We're doing Kirchhoff's voltage law. This is one loop, right? We could find out that across our third load, this is our third load, and this is our first load, or it could be your second. We lose 331.8 with a phase of 24.6 V RMS. And then again, we lose 240 with a phase of 0 V RMS on our first or second load. If we add these up, we can get that the total voltage of the voltage current or the voltage source is 560 with a phase of 14.3. If you want to do that mathematically, if you want to write that out mathematically, use mesh analysis. You can do here that our unknown VS or VS RMS is equal to, or VS RMS minus 331.8 with a phase of 24.6 minus 240 with a phase of 0 is equal to 0. Rearrange that. Very obvious. 560 with a phase of 14.3. The second way, which is what I tried to do, but I got it wrong because I messed up my Z, is using V is equal to IZ. You know the you can simplify this current or this circuit into a single load or Z total of 1.72 plus 0.029J with a current. We already know the current because that's the one coming out of I3. If you look at it's a mess. I'm sorry. If you look at the circuit up here, you will notice that this I3 is the one that's coming out of the voltage source. So that will be our current for this circuit. If you multiply them together, you will get the exact same answer. So those are two different ways of finding the equivalent voltage RMS of the voltage source. They try to curve it with the marking grade, right? Is that some of the questions will have most of their marks near the end, and some of the questions will give you literally half of the marks just for doing like the base amount. Yeah, if you fuck up any steps, you screw up the entire question. However, they tend to be kind of generous on that. So don't think too hard. If you come to the end of a question, you're doing the question, and you think to yourself, man, I feel like I made a signage mistake, or, I accidentally copied over a number wrong. Don't worry about it. Just finish it and come back later if you have extra time. You don't have enough time to review entirely, or you might not have enough time to review it entirely. So spend your time wisely. I got like 4 out of 20 because I had no super node. Oh, that's rough. Realistically, we're all gonna have different answers. Yeah, that's just how hard it is. So that's question 5 done. Is there any part you guys want me to review before I finish up question 5, and we'll take like 5-minute break? Or you think that it's explained okay? Can I just do like essential stuff? Are you saying like you want me to go over the essential parts of power? Oh, sum it up. Okay, so I'm probably just going to sum it up on this page here. So these are the equations that are very important, right? The apparent power is the magnitude of the apparent power is the magnitude of the voltage times the RMS times the magnitude of I RMS. And this is the angle for it. You need to remember that one. This one you probably won't do. These are the formulas for V and I RMS in case you have to convert between I and I RMS or V and V RMS. These are the connections here, right? So real is measured in watts. It's measured in watts. It's written as P average, and it's the average power. Imaginary is voltage, amp, resistance. Q, all that's fun stuff. What does that theta S minus theta V minus theta? Yeah. What does this mean, pretty much? This is, okay, so this is the formula for S, because S is also a complex number. It's going to be VRMS, IRMS, the magnitude of each, with a phase of the voltage phase minus the current phase. So you can't just multiply VRMS and IRMS together. You'll get the wrong phase. You have to do this. And remember, this means magnitude. This hat on top means magnitude here. S is power, right? Apparent power, complex power. When you're putting it into the triangle, Q is the height of the triangle, P is the base, and S is the hypotenuse, right? Yes. So, let me just draw a power triangle here. Oop. This is the phase. This is S. This is Q, and this is P average. This is lagging. If I is greater than if the phase angle of I is greater than the phase angle of voltage, it flips upside down, right? So this is delta V minus delta I. This is P average, lagging. Delta V is greater than delta I. This is Q, and this is S. This is leading. Where delta, did I say delta? I'm sorry. Theta I is greater than theta voltage. So those are the power triangles. Triangle. And just to make it very clear here, you won't be using this formula, really. You should just be using VRMS. Just to make it very clear here. S is equal to the magnitude of S with a phase angle of delta S, or theta S. I keep on mixing it up. So there's your power triangle. This is pretty much it, right? Also, S total is equal to the sum of S's. Same with Q total is the sum of Q's. And same with power average total. AV. So that's it. That's pretty much all that there is to power that I can really think of on my head. The rest of this is just finding V, finding I, finding total impedance. That stuff you've already been taught. So this part here does not matter if parallel or series. That's pretty much the core what you need to know bit for power. Is there anything I've missed? Oh, right. Oops, I left that at the bottom. These are the power factors. This is just trigonometry. You should be able to do that. There. Copy, paste. This is going to be uploaded later, again. So, I think that's question 5 done. Is there anything else that... you want me to clear up or see if I'm missing any part? Can you show the last part of the question again? Sure, question 5 or 6, like total impedance or the RMS value? This is the main part I remember. 6. Okay, here. So we have the let me copy over the impedance of each one so it's clear what's going on here. Actually, I did. Here. That should go up here. Oops, I actually grabbed the top of the eye. So if you look here, we have the impedance of each sort of thing, and then we put it into we find z total. Is there any way to double check this answer on MultiSim with this kind of question? That is a great question. I believe there is. There's probably like a watt meter in there or something, but I don't know if it can tell you the apparent power and the reactive power. I don't. I don't know, to be honest. I would have to really look into it, but I just haven't, so I don't know how to. This is like the only question which I don't know how to simulate on MultiSim. So there's not a MultiSim for this question that I've made anyway. Is it possible for you to go through A and B, my goat? Because I missed it like really quickly. Okay, yeah. So A and B. You mean like Do you mean the first and second impedance block, or these two? Do you mean the questions or the impedance blocks? Oh yeah. So let me just write this here. This is 1. This is 3. I did these in like exact wrong order. But yeah, let me elaborate on this. So here you go. So question 1, you just put down the magnitude. The magnitude is 182,000 voltage amps. That's your apparent power. Your P average is just going to be the sum. So P av total is equal to the sum of P averages. Let me just write tot here. Which is equal to 106,000 plus 40,000 plus 36,000. Let me just specify that I got that wrong because I didn't do enough sig digs. And it's the exact same thing for the reactive power, right? It's the same thing for all of them. Just add up the parts. That's it. Let me take that down here. Q tot is equal to the sum of Q is equal to 21,125 plus 30,000 and negative 48,000. How was IRMS calculated? IRMS, where? You mean here? In the last question? Yeah, so it's going to be I3. If you look at the circuit at the top, we found I3 here, which comes out of the voltage source. So the voltage or the current running through the current IRMS running through this voltage source is the same thing as I3. Are we given I3? No, we had to find it. We found it using Kirchhoff's current law. You see here, we did that I3 is equal I1 plus I2. And to find that, we used this here, that S is equal to voltage RMS times I RMS. And using that, we could find the IRMS running through the first and second block. So we found the current running through here, the current running through here, and using Kirchhoff's current law, you could find I3. Are there any big variations that change how this question is done? Frankly, I think that this is the hardest example. Because you have both, two of them in parallel, you have one in series, one of them is in impedance form, and you need to find the total impedance, the RMS, and on top of that, you need to make sure that you put sig-digs on your calculator, or else you're going to get the exact same answer for the average energy and the apparent energy. So why is the given RMS different from the VRMS that we calculated? The VRMS that we calculated here, for the third one, this here is, if you're that's what you're asking, this is the voltage difference across this. So this is the positive end, and this is the negative end. This is not the voltage difference between the ends of the voltage source.